Case Western Reserve University's Great Thinker Series proudly presents the Origin Science Scholars Program. These lectures are presented by the Institute for the Science of Origins, a partnership of Case Western Reserve University, the Cleveland Museum of Natural History, and IdeaStream, with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. I'm very pleased tonight to introduce Claudia Duran. Professor Rham completed her PhD at the University of Cambridge and went on to do postdoctoral work at McGill University and McMaster University and the Perimeter Institute of Theoretical Physics in Canada. After that, she was a Swiss National Foundation professor at the University of Geneva before moving here to Case Western Reserve. I'm very pleased to have her here to talk to us as the second speaker in our series on general relativity, and this, the 100th year of general relativity, about testing gravity. Please join me in welcoming Professor Duran.
So thank you. This is a cut of a newspaper from almost 100 years old, and about 100 years ago, roughly after the proposal of the theory of general relativity by Einstein, it was described by himself as a theory where only a handful set of people could comprehend its beauty and even test it. And from there, we've gone a really long way. Today, thousands of people are testing the theory of general relativity throughout the planet, and we think we understand this theory so well that it's even been implemented in some of our everyday technologies. So take this TV, for instance. For you and me, this is just a standard technology. We don't necessarily think of that as a machine that tests the theory of special relativity or general relativity. But actually, if you look inside this old monitor, what you will see is a cathode ray tube where electrons are shot in a beam so as to light a screen, a phosphorescent screen at the end of it. And this beam of electron is directed by some magnet around it so as to get on the screen at the right time, at the right place, and to get the beautiful pictures that you like to see on your TV screen. So none of that seems to have anything to do with relativity until you realize that this beam of electron actually travels at 30% of the speed of light. So that's about 100,000 kilometers a second, or about 62,000 miles a second. And at this high speed, you actually need to account for the effects of special relativity to be able to get the electrons at the right place at the right time. And the manufacturers that manufactured the magnets around here so that to properly direct the beams of electrons had to account for the effect of special relativity in doing so. So this is for the theory of special relativity, and for those of you who were lucky enough to be here last week on Andrew Stolley's talk, you probably heard that the theory of special relativity came about when you're trying to incorporate the notion, Galilean notion of relativity with the theory of light or Maxwell electromagnetism theory, or anything that travels very, very close to the speed of light, like the electrons that I was mentioning. And when you put these two things together, you really need to have the theory of special relativity and some small corrections to the way you add velocities, for instance. So that's the case for special relativity. Now, for those of you who were here last time, you also seen that when you have the concept of special relativity with that of gravity or acceleration, in this case, you'll have one or two things. Either we'll have black magic, or we'll have general relativity. And I'll argue for the next 5 minutes how having general relativity is actually the only possibility you can imagine if you don't want to get some gibberish out of gravity and special relativity. And so to understand that, let's have a look at Sandusky great spinning wheel. So you have the spinning wheel turning around, the people on the top who are very excited, and people on the bottom, and they just spin around. So this is my model for the spinning wheel. I'll just take a very simplistic approach for it, where I'll consider, instead of having some people and some carts, I'll consider some buckets, and instead of having people, I'll consider some atoms. And let me consider just two of these buckets. We can do it with as many as you want, but let's imagine we have a bucket with atoms at the top who are very excited. The people on top are very excited, very happy to be there. And we have another bucket at the bottom with atoms which are unexcited. Now, from the laws of special relativity, the atoms on the top, they have a higher energy because they're excited. This energy corresponds to a mass, and it gravitates. And therefore, the atoms which are on the top want to fall down, and the whole thing wants to spin around, bringing the atoms which were unexcited back to the top. Now let's imagine we have a device which is able to unexcite the atoms at the bottom and send the energy back to the top via photons. Now, this photon will excite the atoms at the top, and then once again, by Einstein's special relativity, we'll have that the atoms at the top will be heavier, we'll bring them back to the top, et cetera, et cetera. So you can do that spinning machine as long as you want, and so you have, out of these excited atoms, a perpetual spinning machine. This is a perpetual motion machine by just having special relativity in a gravitational context. So either when you add special relativity with gravity, you have some black type of magic where perpetual motion is allowed, or energy is lost somehow in this process. And of course, the solution is the second one, and that's what is implemented in the theory of general relativity. In the theory of general relativity, actually what happens is that the photons, they get redshifted. We say that they get redshifted, by that we mean that they lose, their frequency becomes smaller, they lose some energy. We say they get redshifted because if you started with a photon, of, for instance, color blue or violet, you would get at the top a photon which is closer to the color red or a smaller frequency. And that happens when the photons are trying to escape the gravitational well from the gravitational pull of the Earth. So if you're trying to send some photons from the bottom back to the top, they will lose some type of energy. They will get redshifted in such a way that when they're back to the top, they actually don't have sufficient energy to re-excite the atoms at the top. And so you don't have a perpetual motion machine due to the redshift. And this is not just some type of bizarre imagination that I just pulled out of my hat. This is actually one of the famous tests of the theory of general relativity. And that test was performed in 1960. That's the the notion of gravitational redshift. And it wasn't done quite with bucket, but actually the analogy is not so dissimilar. You had some excited iron atoms at the bottom, and by sending the photon of the excitation to the top, you could make it so that if the atoms at the top were at rest, they would actually, the photons at top wouldn't have sufficient energy to excite them again. And so this is an experiment that has been done on a tower which is 22 meters high. So the difference was really high, tiny. The difference in redshift between the photons at the bottom and the photons at the top, it was actually 10 to the minus 15. And yet, despite this tiny effect, they observed a prediction from general relativity at the 10% level. And by now, we have some control on this redshift at the level of 0.01% level. So this works in remarkable in agreement with the theory of general relativity. A way to understand why the photons at the bottom, or close to the gravitational, to the center of the Earth, have a different notion of frequency than the ones at the top, is because the notion of time is different depending on where you are in your gravitational field. So the photons in here experience a different notion of time than the ones which would be over there. And this has some consequences, for instance, if you're living on different planets. So our notion of time here on Earth is actually slightly different than the notion of time of someone who is on the moon. Because the moon has a mass which is smaller than the Earth, and so the gravitational field around the moon is slightly smaller than that around the Earth, and therefore your notion of time on the moon goes faster, very slightly faster than the one on the Earth. And so the effect is tiny, of course, but if you spend 1 century on the moon, that would actually correspond to 1 century minus 2 seconds on the surface of the Earth. So that's a tiny effect, but we'll see, that will become important. The opposite happens, for instance, if you send your friend to Jupiter. Jupiter is much more massive than the Earth, so if you are on the surface of Jupiter, and you spend 1 century there, that corresponds to 1 century plus 1 minute on the surface of the Earth. So that's 1 minute in a century is not gigantic, but if you are now on very close to the black hole of the interstellar science fiction movie, the mass of that black hole can be so large that if you spend just a few hours near that black hole, that may correspond to many years for an observer close to the Earth. And so that might not seem like, this seems like science fiction. Of course, we're not living close to a black hole, so this may not have a big impact on our everyday life. But let's just imagine the satellites, precisely the GPS satellites, which are 12,000 miles above our head. These GPS satellites, because they're living slightly further away from the surface of the Earth, they feel a gravitational pull which is slightly different than us, and therefore they have a notion of time which is very slightly different than our notion of time. It's a very subtle difference, but this subtle difference has actually a big impact because the GPS wants to, with this GPS satellite, you want to have your accuracy on Earth with a very good precision. To have a precision of the order of 10 inches at the surface of the Earth, you will need to have nanosecond precision on your notion of time. But due to the general relativity, due to the general relativity effects between the surface of the Earth and the satellite feels a notion of time which, over the lapse of one day, correspond to 30 microseconds difference. So 30 microseconds, that's 0.000038 seconds, is really not a lot over the lapse of one day. But actually, 38 microseconds, that's 38,000 nanoseconds. So this is 38,000 too many seconds, nanoseconds, to have the accuracy that you would want to have to be, that GPS actually tell you to get your accurate precision on the surface of the Earth. So if one hadn't accommodated for this effect, you could well be, after a trip of a few hours, a few miles away from your correct precision if your GPS device hadn't accommodated for this correction from special relativity, because the GPS satellites are moving with respect to us, but mainly from general relativity because their notion of time is slightly different than our notion of time here on Earth. So we've gone a long way from technologies on our everyday life that uses effects from special relativity to now technologies that we all use at the level of GPS for a smartphone that use knowledge of general relativity in order to get the precision that we want to have from this device.
I just want to know how that calculation come about, that the differences in time.
The 38 microseconds. So you have two effects. You have an effect from special relativity. If you were there last week, Andrew Tolley showed actually the exact formula to accommodate for velocities correction. So you just need to take this formula. That's the accommodating for the velocity of the GPS on orbit around above our head. That's the 7 microseconds per day. For the effect of general relativity, this effect of minus 45 microseconds a day, you really need to see that and Andrew Tolley last week introduced the notion of the metric. Your notion of metric does depend on how far away you are from the center of the Earth or from the surface of the Earth. And so from this metric, you can see how clocks would tick at a given distance from the surface of the Earth or from the center of the Earth, and you can compare that with an observer on the Earth.
Could you maybe explain again about the Ferris wheel? I think people...
You want to get it again?
Just a little, yeah, just again, a little bit about the Ferris wheel.
So did you understand the perpetual motion machine? Let me try again. So you have, let's imagine, I'm not recommending, although you could try to do that at home. Let's imagine you have some excited atoms high up on your gravitational field, and some other atoms, the same type of atoms, simply they're not excited. And by excited atoms, I mean some atoms for which the electrons are higher up in the energy level. So they carry more energy, these atoms, than the one on the green one at the bottom. Now, from special relativity, energy is connected to mass and gravitates. So these atoms, the bucket filled with excited atoms, will want to flip down, while the ones at the bottom will want to go up, because the excited atom feel a gravitational pull which is stronger than the ones at the bottom. So you'll have a twist like that. Now you end up in a situation where you have unexcited atoms at the top and excited atoms at the bottom. And now through some physical device, you unexcite the atoms at the bottom. By that, the electrons you bring them back to the lower ground state, or you just wait for them to do so spontaneously. And you make sure that the photons that get released when this unexcitation happens, you send them back to the top. And you catch these photons from the atoms at the top, so that then they get excited. And so the atoms at the top now are the excited atoms, and they are the ones that carry more energy, therefore more mass, and therefore would want to make the whole thing spin down again. And you do so. It might be as quick or slow as you want. It doesn't matter. It's the idea that it's a perpetual motion machine. If you could really bring the photons from the bottom back to the top without losing energy in these photons. And that doesn't work out thanks to the gravitational redshift.
Thank you for joining us. You've been watching Dr. Claudia Duran discussing some of the earliest evidence for general relativity, Einstein's theory of gravity. For more information on the Origin Science Scholars Program, please visit the Institute's website at origins.case.edu. In the next part of the talk, Dr. Duran discusses curved space-time. Now, back to the talk.
Last week, Andrew Tolley also introduced the notion of general relativity as being closely connected to that of curved space-time. In a curved space-time, you can think of the patching together of local inertial frames. Locally, you might not realize that you're living in a curved space-time, but it's only when you talk with your neighbor that notion of curvature enters. And that's the same thing on the surface of the Earth, and that's why for so many years people thought the surface of the Earth was flat. If you just look around here, the surface of the Earth looks pretty good, pretty flat. It's only when you're looking around the Earth, when you're traveling a lot, or when you're trying to make a map of the surface of the Earth, you see that it's very hard to glue different pieces together. And that's the notion of curvature, the curvature on the surface of the Earth. So this sphere, for instance, has curvature, and the existence of curvature has many distinctions observable that people have gone away and test for. So let's look at this sphere, and let's imagine that you want to bring a little vector along with you on a walk around the Earth. Or that sphere. So let's imagine you have a little magnet, for instance, that points out in a direction, north-south, and you, for a reason or another, you want to walk around with this little magnet. So you'll go around on the equator for a little while, and then you'll go up to the North Pole, and then back to the original position, just like that, and you want to carry this little vector, this little magnet, the best you can throughout your walk. So you'll do so like so. And you're really thinking you're keeping the direction of your magnet, or you're keeping the direction of your vector the same throughout your walk. And yet, when you come back to your original position, you have a change in your vector. You have an angle between your original vector and your final vector. And this angle is not your fault, it's the Earth's fault. It's due to the fact that you had curvature on the surface of the Earth, and the change of angle here is directly related to an amount of curvature enclosed in that loop. So that might seem a little bit abstract, but actually, this is one way to tell whether or not you have curvature. You just bring along a little vector, and then you'll see if you have some difference in angle. Well, this seems a little bit hard to test, but it's precisely what people have done in current tests of general relativity. So to understand how that can be implemented for the curvature of space-time, not just of space, but of space-time, due to the existence of the Earth. Let's imagine a little bit how we can think of the space-time curvature around the Earth. And once again, curvature is really coming about from patching different regions which may look locally flat. And I can create some notion of curvature by taking a flat space-time and then taking out some wedge and then trying to reglue them together. What I'll get out of that is this type of cone where you really have a notion of curvature which is there. It doesn't look like in this picture, but this is not so dissimilar than the curvature, the space-time curvature around the Earth, due to the presence of the Earth on our space-time. So now for that curvature around the Earth, you can do the same thing and bring along a vector. It can be a little magnet, or it can be the precession of a gyroscope. And that's precisely what has been done in this Gravity Probe B experiment, the Gravity Probe B satellite, which is actually gyroscopes that point out in a given direction. They're orbiting around the Earth, and after one orbit, you will see, or many orbits, you will see a very subtle change in angle due to the curvature coming from the Earth. This change in angle is very subtle, is very small, corresponding to 6,000 milli-arcsecond per year for the effect that I just mentioned. And there's an additional angle coming from the fact that on top of that, the Earth itself is spinning. So this is what we call a frame dragging effect, which is an even more subtle effect like this. So this 6,000 milli-arcsecond per year, that seems like a very subtle effect. Just to give you an idea, that corresponds to around 11 miles, looking at an angle for 11 miles on the surface of the moon. That's roughly the equivalent of an angle per year, though. So this was on over many years, of course. And so to give you an idea of the success of this experiment, let's look at the results from the different gyroscopes that they obtained. So this line here corresponds to the angle from the movement of the vector due to the fact that the space-time vector was curved. And then this one due to the frame dragging due to the fact that the Earth is itself spinning. And then these different circles corresponds to the observations. The combined result is this black line, and the GR projection is the black point in the middle of it. So this is an impeccable agreement, and it's even more an impeccable agreement when you actually compare to what would have happened if you hadn't had a GR. So this is not just some fluke of chance. This is really a beautiful test for the theory of general relativity, and which puts general relativity in very good grounds. And nowadays, it's extremely hard to modify this theory of general relativity and yet be consistent with these observations. So now that we understand how gravity behaves so well around the Earth, let's move on and let's look at the solar system. And people have studied the motion of planets around the solar system for hundreds of years, and we know that they follow Kepler's laws of motion pretty well, actually very, very well. So this is a Kepler orbit. Let's imagine this is the Sun at the center, almost at the center, and then this is Uranus spinning around the Sun. It's following almost an ellipse like that. Only there's a subtle difference, and the difference is very much exaggerated here, but actually the orientation, the direction of the ellipse is changing ever so slightly as a function of time. So it's not a closed orbit, it's actually changing very so slightly. And many observers have seen that effect since already the 18th century, and this is something very well documented, and we can understand that by the existence of maybe another planet or another object nearby, for instance Uranus, which creates a small additional gravitational pull, and then change ever so slightly the orbits of that planet. And so for the case of Uranus, this has been done with a very good precision, and Leverrier in 1846 was the first one to predict precisely the mass and the position of the supposed object that should be there that would explain the motion of Uranus around the Sun. And he sent a letter to Gall, and then the same day, Gall had a look with his students in the direction that Leverrier had suggested, and within 1 hour of observation, they found the planet Neptune. So this is a beautiful success for Newton's laws of motion and the Kepler laws of motion. And this has worked beautifully well. For Uranus, actually, while Neptune was found exactly where it was predicted by Leverrier, there was some very small additional irregularities in its motion that could later be explained by the existence of Pluto. And Pluto was indeed discovered in 1930 from the motion of Uranus. So encouraged by this beautiful success, Leverrier also knew that there were some irregularities in the motion of Mercury around the Sun. And there as well, it followed almost some orbits, but the direction of the orbits was changing ever so slightly as a function of time. And so Leverrier postulated the existence of a planet. This time that planet had to be between the Sun and Mercury, or in the distance between the two. And that planet was actually discovered in 1859 by Le Cabots. And it's the well-known planet Vulcan that we all have heard about, of course. And so all of that is a beautiful success for Kepler's law of motion and Newton's law of motion. Only the planet Vulcan does not exist. Well, it does exist, but in science fictions, which came out afterwards. So the planet Vulcan is not, since it doesn't exist, is not at the origin. That cannot explain the very small irregularities of the motion of Mercury around the Earth, around the Sun. And we had to wait actually till the theory, Einstein's theory of general relativity in 1915 to explain fully the motion of Mercury around the Sun. So this motion, this orbits of Mercury around the Sun is actually the first test of the theory of general relativity before even the theory of general relativity was discovered. So it's one of the best successes of the theory of general relativity. And the effects from general relativity in the change of the orbit of Mercury around the Sun are very subtle. They're much smaller than the effects from the other planets in the solar system, including Venus, the Earth, and Jupiter. But they are there nonetheless. And to give you an idea of the effects, they correspond to 23 displacement in the position of the planet of 23 kilometers every orbit. Now, to put that in perspective, this is a passage of Mercury in front of the Sun. You have to compare these 23 kilometers, knowing that Mercury is a few thousand kilometers across. So it's a very subtle difference that you need to be able to detect. And so within the lapse of just one orbit, the difference is absolutely ridiculous, and there's no way you can really detect it, definitely not with the naked eye or the technology at the time. However, it's an accumulative effect. So people have been observing Mercury for such a long time, and this effect from general relativity is just adding up and adding up and adding up, that after 150 years, it's a clear signal that people can observe, and now it's in complete agreement with what we observe in the position of Mercury around the Sun, and that's been done for all the other planets in the solar system. We understand them extremely well, taking into account the effect from general relativity. Okay, so these are the orbits of planets around the Sun. And they follow some orbits which are ellipses and then change very so slightly in direction. But I'm lying to you a little bit here, because if that were really the case, then again we would have a perpetual motion machine. Again, we would have a planet that could go around the Sun until the end of the universe. But actually, the situation is slightly different than that. For planets, this is an extremely good approximation. It's almost really there. But if you take two objects which are of more comparable mass, so let's take two stars of masses of about the Sun, for instance, their motion is so that actually if you want the length of the perihelion, or the shortest distance between these two objects, or the longest distance between these two objects, it actually shrinks every so slightly as a function of time. So that's why we don't have a perpetual motion machine. You do actually lose some energy throughout this process. And in the case of a planet, which is a very small, very light object around the Earth, you cannot notice that object. But for two comparable mass objects, like two stars, you can actually notice that object, and that has been measured precisely. This is some real data from a Hubble stellar pulsar. This is a binary pulsar that people have observed 25 years ago, or even more. And the blue line is the expectation from general relativity, from the fact that you expect these two objects to get every so slightly closer and closer together, and the red point corresponds to the observational data. And once again, they're in impeccable agreement with one another. In this case, we have to understand the loss of energy through the emission of gravitational waves. The gravitational waves are to gravity what electromagnetic waves are to light. So we are usually more familiar with the concept of light and electromagnetic wave. The photon, the particle carrier of the electromagnetic force, it can also be thought as an electromagnetic wave, and we can, of course, see this electromagnetic wave. In the gravitational picture, if you have a gravitational force between two objects, let's say a star and a planet, or between two stars, you have this force can be thought as being mediated by a particle, in this case is the graviton, and this graviton can also have a gravitational wave effect, which you can produce gravitational wave when you have accelerating charges in the context of gravity. The context of gravity, by charges, we really mean mass. And so when you have accelerating mass, they produce gravitational waves. And gravitational waves emitted by this, in the space-time for these two stars, correspond to a loss of power, and is the reason why the two objects are going slightly towards each other. They're doing so at a very small rate of 1 centimeter per year, but they're still doing so ever so slightly. So this binary pulsar, this two-star system going close to one another, is one of the best evidence for the existence of gravitational waves. But people are also trying to detect these gravitational waves directly on the planet. And so to get an idea of what that will mean, let's imagine we had a gravitational wave. For instance, one of the gravitational waves emitted by these two stars, but maybe a stronger one. This would be a really strong one, emitted by black hole collider. If a gravitational wave was going through this room, it would deform an object which initially would be around, it would deform it like that. This is, of course, very much exaggerated. And so people throughout the planet are trying to build interferometers so as to be able to detect these gravitational waves directly, to have a direct detection of gravitational waves. So these are vacuum chambers. There are two vacuum chambers with light going across, and they're really trying to measure the distance between in these tubes, which are about 4 kilometers long. The change in distance, if a gravitational wave was coming through, is ridiculously small. It's smaller than the charge radius of a proton. So it's ridiculously small, and yet they think they have the technology sufficient to do that. And throughout the planet, there are different interferometers. People are trying to look for gravitational waves, and we are really helpful that something like that will happen in the near future.
What causes the gravitational redshift?
What causes the gravitational redshift? The fact that the notion of space and a notion of time is not something universal. The notion of space and the notion of time depends on, for instance, the curvature of your space-time. So it depends whether you're very close to a massive object or whether you're in an interstellar medium with nothing around you. Your notion of time will be different. And so if you're on the surface of the Earth, or if you're very far away, your notion, or further away from the surface of the Earth, your notion of time would be different. And so if you emit a photon where you think you have a given frequency, and a frequency is a number of ticks per second, for instance. But if your notion of time is not the same for you and another, a satellite or something else further away, what you think a given frequency is different for the other observer. And that corresponds to that change of frequency and therefore to that redshift.
Can you go back to your slide with the Sapphire beam splitter experiment, as fancy as that sounds? Is this something that can be done within a room, this experimental setup? What is the distance between?
These arms. These arms are about 4 kilometers long. Yeah, so these are these pictures here. In these arms of about, so that's 2.5 miles long, you want to measure a change in distance through the passage of a gravitational wave, which is smaller than the charge radius of a proton. So it's a ridiculously small distance that you already for 4 kilometers long arms. So doing it on a smaller range would require having being able to measure a difference in distance, which is ridiculously small. But you can do it on much bigger scales. So there are some proposals to do that in space, where the arms could be much longer, and therefore you could see a much larger difference.
Is the period of a gravitational wave constant, or are they variable?
The frequency? Yeah, it can change a little bit. So you can think of the gravitational waves for this type of observation. For matter, you really think of them coming from the collide of merging of black holes. So in the original phase, the frequency will be more or less the same, but then in the final phase, it really speeds up, and so the frequency it gets different, yeah.
Can you explain again why Mercury's special and it was different in predicting its orbit versus the other planets?
Mercury, they had already reached the level of precision where you needed to account for the effect of general relativity, because it's the planet which is the closest to the sun. So for the other planets, they are further away from the sun, and therefore the effect from general relativity are a little bit smaller, and it took longer to reach the level of accuracy to be able to see them. But for all the planets in the solar system, you need to account for these effects of general relativity. And that is very well understood. So even the motion of the Earth around the sun, you need to account for this, what we call advance of the perihelion, due to the effect of general relativity, to really understand its motion. And people do that for the moon around the Earth as well. So Mercury is it's not only Mercury that has these effects. All the other planets and all the other objects in the solar system have these effects. It just was the first one.
We hope you've been enjoying the Origin Science Scholars Program with Dr. Claudia Duran. In 2014, Dr. Duran was the inaugural Emmy Noether Fellow at Canada's Perimeter Institute for Theoretical Physics. In the second part of our talk, we learned about gravitational waves and gravitons, the particles that are believed to carry gravity. In our final segment, Dr. Duran will discuss black holes and the evidence for their existence. Now, back to our talk.
Okay, so for this last part of the talk, I'd like to bring you through singularities as predicted from the theory of general relativity. So general relativity does predict singularities, and the first type of singularity that it predicts is black holes. So let's look a little bit at what a black hole would be, and for that let's imagine the notion of gravitational pull or gravitational attraction. So if I want to send something, like this thing or an apple, I'm not very strong, so I can try to send it very, very fast. It will come back on Earth. But if I have the right resources, I can build a shuttle station and put the apple on top of it, and then fire the shuttle and send that apple not even on orbit, but really send it out of the solar system. And if I really send it with a strong enough force, I can send it out of the galaxy even if I want to. So that you can escape the gravitational pull of the Earth by sending the object with a sufficiently large velocity. If you're trying to do the same thing on the surface of a black hole, it doesn't matter how powerful your shuttle is. It doesn't matter how powerful your technology is. You can't wait 1,000 years if you want to build better technology. It doesn't matter. You will never find a technology strong enough, sufficient enough for you to be able to escape the gravitational pull of the black hole and to send this apple away from the black hole if you are at the surface of the black hole. And so inexorably, the apple will fall into the black hole. Now you can imagine the similar type of experience with light. If it's dark here on planet Earth and I shine, if it's night, and I shine a flashlight outside towards the sun, well, you might get reflected by the clouds, but let's imagine it's a very beautiful sky night out. And the light can really escape the gravitational pull from the Earth, and you will never see that light again. It may, if there's no dust, no clouds, and nothing in between, it may even escape the whole gravitational field of the galaxy. So light can go, you can travel an infinite distance away. Now, if you want to do the same thing on a black hole, you won't be able to do. You won't be able to if you are at the surface of the black hole. And so this is a slide from last week, for those of you who were here last week. And light actually does feel a gravitational pull as well. And this was one of the first tests of the theory of general relativity, gravitational lensing. If you have a star far away, and the beam or the light from this star is going very close to the sun, it will actually experience some deflection. and there's a deflection angle between what its position would be had it lived in flat space, had the sun not been there, and what it is if the sun is there. So that's the deflection of light, to tell you that light does feel the gravitational pull of any object, in the sun in particular. And it does feel the gravitational pull of black hole as well. So now imagine if the deflection angle is so large that actually you don't even see that light. If it just fell inside the object. That would be the case if that object was a black hole. And so if you're in a black hole and you're trying to shine light away, it doesn't matter, it will still fall in the black hole. There's nothing you can do from the surface of a black hole to be able to send away from the black hole. So a black hole, we call it a black hole because nothing can escape its gravitational pull, not even light. And that's a picture, artistic picture of a black hole. But at that surface here, this is what we call the horizon of the black hole. That's when light, that was the last time light could have escaped its gravitational pull. And if you have light or any other object inside this black hole, it will no longer be able to escape the gravitational pull of the black hole, no matter how hard you try. But it doesn't mean that this is science fiction. This is really science. The theory of general relativity can really be trusted at the horizon of the black hole and even a little bit inside. We can trust the theory of general relativity here. We can understand what would happen if we were sent inside a black hole. The theory of general relativity tells us precisely that. And it also tells us that it is a valid theory in that region. And it actually not something, this is actually something that we can check. And black holes, even though we haven't detected light coming from that, we have some strong evidence that black holes do exist. We have some strong evidence that black holes exist at the center of almost all the galaxies that we can see. So these are the light correspond to the orbits of stars at the center of our galaxy, and we see that it's spinning around something which we don't see. And this something has a mass which is equivalent to almost 1 billion solar masses. We don't see it. And we know it must have such a large mass because it's deviating the trajectory of the stars around it. So that's how we can estimate the mass of this object there. It must be a black hole. It cannot be a neutron star or anything like that. We would see it. It's something so massive and invisible, it has to be a black hole. So black holes are not just for interstellar science fiction movie. They actually do exist, and we do believe that they are present at the center of almost all the galaxies that we know of. So singularities do exist in a theory of general relativity. It does predict it. So while we're looking at stars, if we look at stars around us, and that has been done for almost a century, well, of course for a long time, but if we look at stars around us, on average, we see that the stars seem to get away from us. And it seems that the further the star is, the quicker it wants, or the fastest it wants to get away from us. And that's true in all the directions that we can see. And that doesn't mean that we're living somewhere special in our universe. Rather, it means that our universe is expanding. And so if our universe is expanding, if you're going back in time, and I don't mean let's go back in time, I mean let's have a look at how the universe was behaving in the past, it must mean that the whole universe came out from one point. And that corresponds to a Big Bang singularity. There are a theorem in the theory of general relativity that tells you, because the universe is expanding now, there must have been a Big Bang singularity originally. The theory of general relativity predicts this singularity. And it doesn't mean that this Big Bang singularity happened somewhere in the universe. This Big Bang singularity happened everywhere in the universe together. It's no special point in the universe. All the points in the universe came out from that Big Bang singularity at the same time. And so we think we understand the behavior of a universe up to a fraction of a fraction of a fraction all the way up to the Big Bang. So very, very close to the Big Bang. We do believe that we understand the behavior of the universe, and from everything thereafter, for instance, the cosmic microwave background, where you might have heard some talks about, and the formation of structure and all the formation of everything that we know in the universe, we do believe that we understand that very well. And we do believe that it all merged at the beginning from a Big Bang singularity. So whether it is in the notion of black holes or Big Bang singularity, or it could even be for later on, the theory of general relativity predicts the existence of singularities. And the singularities can be cosmic singularities, black hole singularities. It could even be that ultimately the universe will recollapse into itself, and that would correspond to a future singularity. Now, data tells us, observation tells us that this seems unlikely now, but it could be that there is a big rip singularity, that the universe is not only expanding so much, but this expansion is accelerating and accelerating even faster, so that at some point, space-time will not be able to carry that acceleration anymore, and you'll have a big rip singularity. So there could even be some singularities in the future. And GR predicts all of these type of singularities, but what we know is that at the singularities themselves, we can no longer trust the theory of general relativity. So the theory of general relativity is beautiful in that it predicts singularities, and it tells you, well, I'm not going to be valid there anymore. So it predicts its own failure. It's the most beautiful theory that you can think of. It's not like the theory of Newton and gravity, where you had to go to observation to say, oh, now there's a failure of my theory. I need to implement a new theory that tells me what's going on in this type of setups. The theory of general relativity is unique in that it tells you, I'm going to be valid up to that point. I'm going to predict that something happens there where I'm not going to be able to tell you anymore what's going on. And so from the very theory of general relativity, we know that there must be something beyond general relativity. And so I like to finish almost there by saying that it's been a very successful 100 years of general relativity where we think we understand the theory extremely well, and we also think we understand that it has to be now extended to a more fundamental theory that will allow us to understand what goes on at the singularities themselves. And this is something that people are trying to work out throughout the world. And let me just finish where I started from. 100 years ago, it was believed that the theory of general relativity was really useful only to a handful of people. 12 wise men was the quote in here. And I'm very proud to say this is no longer the case. The general relativity, testing general relativity and using general relativity has really become a worldwide endeavor. You have these interferometer experiments throughout the planet. So in all the continents, you have interferometer trying to get to detect gravitational waves. This is really a worldwide endeavor which includes thousands of people. And I'm also very proud to say you don't need to be so wise anymore to study general relativity. Many people can do it. And you don't necessarily need to be a man anymore.
You've shown us that light can be bent by gravity. And you've shown us that on the surface of or pretty close to a black hole, if you shine light up, it turns around and goes back. So it has to come to a stop at some point. That means the speed of light is not a constant as we thought 100 years ago.
Well,
and demonstrated in this university.
Yeah, very good.
Could you comment on that?
So when I say we understand what goes on when you enter a black hole, it doesn't mean that it's very natural what happens when you go inside a black hole. When you are entering inside the horizon, your very notion of space and time switch around. So even your notion of velocity inside or speed of light inside the black hole can be slightly different. But it is true that once you are getting close to the singularity in here, the very notion of particle is probably not a good one anymore. And so it's very likely that the notion of Maxwell and a constant velocity for the speed of light is probably not the correct one anymore. But you will really need to understand what glows that new theory, what is in the new theory which is correct at the singularity itself, to understand what happens with these particles and what happens with what we thought was the speed of light. And the very notion of causality at that point. But going through here, at the horizon here, the light doesn't stop here. Nothing as an observer, nothing too dramatic happens here, apart from the fact that you probably stretch apart.
You said that most galaxies have a black hole in the middle. What else could be in the middle?
What else can be in the middle of a galaxy? Apart from a black hole or on top of a black hole?
Instead of a black hole, what else could be in the center?
Yeah, it's difficult to it's difficult to imagine anything else but a black hole. Yeah, because you need to have so much mass in such a small region that you have to create a black hole. It would collapse under its own gravitational well. You can't expect to explain the motion of stars at the center of the galaxy through dark matter, for instance, because you would need to confine so much dark matter in such a small region of space that even if it were made of dark matter, it would still create a black hole. The photon is a massless particle, and so how does gravity interact with the photon? And already from the laws of special relativity, there is a relation between the notion of energy, a photon does carry some energy, and the notion of mass. So this is probably the most famous Einstein's equation. There's a relation between the two. This is coming from special relativity. So already there you can see that there's a connection between photons and a gravitational field. Now, in that picture in a curved space-time, a massive or a massless particle, they still follow some specific, what we call geodesic specific trajectories. And they might not be exactly the same whether they're massive or whether they're massless. So they might not be exactly the same for a photon or for an electron, but they do feel the curvature of space-time. When we draw something like this, the fact that space-time itself is curved tells you that your notion of what a straight line is not your naive notion of what you would have thought in a flat space-time. So the distance between that point and over here is actually not a straight, what you would have done, just a straight line like that, is actually, in this case, this type of curve. This is your notion of a straight line. And light follows what it thinks is a straight line. And that corresponds, so it's influenced by the gravitational field, because the gravitational field corresponds to a curvature of space-time.
Could you say something about the results of the searches for gravitational waves? Are there any clean results, or what do you think the prospects are now?
So there are rumors. I cannot say anything about these rumors. I don't know anything about these rumors. So all the way up till now, although people were hopeful to detect gravitational waves, it did make sense not to detect gravitational waves. We did not expect to detect gravitational waves unless something very unusual was happening. But a month or two ago, Advanced LIGO switched on, and then if our understanding of how things work, of how black holes are merging to one another and how gravitational waves are produced and vehiculated all the way to here, we do expect in a normal scenario to start to be able to detect such events on a regular basis, maybe once a week or something like that. And so we are very hopeful that now, since Advanced LIGO has been switched on, that very quickly we'll be able, that they will detect gravitational waves. But so far they have made no announcement. But even if they had detected gravitational waves, they wouldn't tell us before being very sure. So I cannot comment. I don't know.
This lecture is part of the Origins Science Scholars Program of the Institute for the Science of Origins, a partnership of Case Western Reserve University, the Cleveland Museum of Natural History, and IdeaStream. It has been brought to you with the assistance of Case Western Reserve University's College of Arts and Sciences, Siegel Lifelong Learning Program, and MediaVision. For more information on the Origins Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.